Okay, everybody, thanks for joining us here. We're only a couple of weeks into the semester and or not into, but left of the semester. So we are kind of getting down towards the end of things. So I know things are getting busy, but thanks for joining us. There's a couple other events going on and around campus today, in particular too, that Nicholas Jones is a part of. And I didn't realize we had scheduled this at the same time, but I guess that works out. So today we have graduate student Nicholas Jones, who I don't work with, but we are in the same division out of the National Security Institute with the Mission Systems Division. So today, a EMCCD simulator in MATLAB is our. So without further ado, I'll let you do it.
Thanks for the introduction. So, as reflected in the title, today I'll be talking about a EMCCD simulator that we've been putting together in MATLAB. And to start off with, I'll talk about the motivation for this work that we've been doing. So this work is actually stemming out of a instrument development program here at Virginia Tech, where we are developing a CubeSat form factor stellar occultation instrument for measuring nitric oxide in the polar night. So this is going to allow us to do some investigations into key heliophysics science questions as we explore how the upper atmosphere and space weather are coupled. Now, this program is being funded out of NASA Rose's H-Tides, and our PI is Dr. Harding. Now, the work that we're doing is actually building off of previous work that was undertaken by Virginia Tech as part of the Polar Knox program, which was led by our co-PI, Dr. Bailey. That was a sounding rocket mission that had a much larger instrument. And so what we're trying to do is reconfigure this into a form factor that fits in the CubeSat, and this will allow us to take measurements throughout polar winter. Now, we are also partnering with our co-investigators out of NASA JPL, and they'll be providing the camera electronics for our instrument. Discuss a little bit of the science. So nitric oxide is produced by reactions in the upper atmosphere between excited atomic nitrogen and molecular oxygen. Now, the energy to create the excited atomic nitrogen is provided in the auroral regions by precipitating energetic particles. And this is able to break apart the strong bonds of molecular nitrogen. Now, the key part of the loss processes that regulate the amount of nitric oxide in the upper atmosphere is actually related to photodissociation. Now, in the polar night, we go for long periods of time where there is no light in the upper atmosphere. And so this part of the loss process is lost. And so what we see is nitric oxide is actually able to build up in the upper atmosphere. And because it's not being broken down, its lifetime is long enough that we actually see it able to be transported downward in the atmosphere, where it can interact and catalytically destroy ozone. And so this sort of ties together what's going on in space and space weather with the actual atmospheric composition of what goes down at lower altitudes. So the technique that we're going to be using is the stellar occultation technique. So we're using starlight as a signal source and seeing how it is attenuated as it passes through the atmosphere to relate this to the amount of nitric oxide. Now, for our target column density, we're looking to try and get a signal noise ratio of 1 on 2e to the 15 molecules per centimeter squared nitric oxide, 3 kilometer altitude resolution. The resulting attenuation is quite small. You see in the figure in the upper right, for 2e to the 15th, which is right around here, we're looking at less than 1% of attenuation. And so combine this with the fact that our altitude bins are being scanned over in about 1 second, we need to be able to build up very high SNR on our starlight measurements very quickly. And so this introduces many challenges in terms of the instrument design, because we are both working with reduced size, weight, and power constraints, but we also need to be very sensitive to the light that we're looking at. And so for us, that's going to be 215 nanometers. And this coincides with an absorption feature of nitric oxide. And so how we're accomplishing this is we are developing a custom filter with Chirion that'll provide us a very narrow as sensitive to changes at that wavelength as possible. We're also working with UV specialized optics that we're trying to get from more to the more national labs. And then the key contribution from our co-eyes is going to be delta dose EMCCD with UV specialized anti-reflection coatings. Now, what's important about using EMCCD is it allows us to use photon counting, and this virtually eliminates the read noise from our measurements. So that's sort of the background and motivation of why we want to use EMCCD. It's really what enables us to make those high precision measurements on the starlight that we need to be successful. Now, start talking about the EMCCD themselves. So EMCCD stands for electron multiplying charge coupled device. Sometimes you see these referred to as low-level CCDs. And essentially, they are the same as your standard charge coupled device, but they have an additional output register has been added on. You can see that here, that features a multiplication register. And this is what applies the gain to the signal before readout. So CCDs, they're composed of individual pixels. And how charge is generated is that incoming photons are creating charge, so electron hole pairs, through the photoelectric effect. And these electrons are gathered within those pixels. So throughout this presentation, I'll kind of be going over some key parameters of EMCCDs. That'll help us to understand what we're looking at in the simulator later. So the first one is interacting quantum efficiency. And this characterizes how many of the instant photons actually interact with pixel to create charge. Then we have another parameter that's important here, which is quantum. This characterizes the number of electrons produced per interacting photon. Now, something I will note, just for general knowledge, is that the silicon energy band gap of about 1.1 kilohertz, this actually limits what wavelengths you can look at with the CCD. So in this case, you really need light that is more energetic than what you get at 1100 nanometers. Beyond this, the light just kind of passes through, it doesn't have enough energy to create electron hole pair states. So we're generating charge through the photoelectric effect and gathering them in pixels in the image area that we see here. How do we actually transfer that charge out? Well, we do it through the clocking process. So if we look at the diagram on the right, we start by integrating our signal on the pixels. So a charge is being generated and collected. And what we see is that it's going to fill in these potential wells for each pixel. And then what we can do is we can manipulate the potential under each of these phases of each pixel, and so march our charge along. So first we can collect our charge in one phase. Then we can enter the next clock cycle. So we see it's marched along just a little bit from where it originally was. And then we can repeat that to transfer it into the next pixel. And then by repeating that again and again and again, what we can do is we can march it out of that imaging section into the readout register, and then with the same process, march that charge out to the output node of the detector. Now, the efficiency of this transfer process that's characterized by the charge transfer efficiency. So that just describes for however much charge you have in your potential well, in your charge cloud, how much of that is going to be transferred over to the next well. And so one thing we'll note, and something we'll see later, is that poor CT performance causes smearing of the image as charge essentially gets left behind with each transfer. And so for context, if we consider what a device looks like, there could be thousands of pixels inside this imaging area alone, and then another 1,000 as you've marched through the output register. So you need to have very good CT performance, typically on the level of 6.9. So 99.9999% of your charge being transferred to make sure you get something that is usable on the way out. if you only transferred something like 90%, by the time you got through all those transfers, your charge would be smeared out over the entire array. So that's how we transfer the charge. Now, for a standard CCD, the next step would be the actual charge measurement process. And this just takes it through an output node, and here is where we actually measure the charge and then digitize it. You can start working with the measurements in our computer, downlinking them, working with them, whatever you want to do. So this is the stage where the read noise is applied. However, what makes the EMCCD special are those additional electron multiplying pixels in the readout register. So what this allows us to do is, in a process very similar to the charge transfer process, we are able to accelerate the charge by applying relatively high voltage, so something around 40 volts, underneath one of those pixel bases. So that allows us to get impact ionization and be multiplying that charge. And this provides a unique gain on our actual signal of interest that isn't reflected in the readout noise. And so what this does is allows us to amplify our charge measurement well above the levels that are being applied by the readout noise and make it insignificant. Now, how this works is that each stage has a probability P of being multiplied, and we can calculate our mean gain, G, through this first equation, where you can see we're taking 1 plus P and raising it to the number of stages that we actually have involved in the multiplication process. And so typically, this probability P is quite small, but with hundreds of stages, we can reach relatively large gains. In the plot on the right, we see that we are able to achieve, mean gains of about 1,000 over the course of, in this simulation, 604 elements. Now, I'll return to this last equation here later. This equation is actually describing the output probability distribution function for a given number of stages in a given mean gain, or the number of input electrons X to the output register. We're going to apply that later for our camera characterization methods and see how we do that. Now, like any device, there are important noise sources that we have to consider on our measurement. So the first is the shot noise. This is just the inherent statistical uncertainty in the arrival of photons incident on the detector. So say you have an arrival rate of 10 photons per second. During any given second, you might have 9, you might have 11. There's uncertainty associated with that. The next is dark current. And so this is a result of thermal energy of electrons sometimes being high enough where they can cross the band gap of silicon and then add themselves to the charge cloud. So how we mitigate this is by cooling the detector. We can see in the graph on the right, just how cool we have to get these things. The applications that we are considering, we're looking at something around the -85°C level. Then the next one we consider is read noise. So this is again just something that is applied as part of the readout process. The other consideration that we have to worry about is clock-induced charge. And so this is something that's actually only significant for EMCCDs. On standard CCDs, this isn't something you typically see as a dominant noise source, if you can recall. But with EMCCD, when we're actually doing the multiplication process, we are applying very high voltages very rapidly to this device. And so what we can get is that holes within the CCD material, they're also being accelerated, and they can actually create additional charge outside of that is normally created through the EM gate process. And this is again another additional noise source. Finally, we also have phantom noise, and this is noise due to, again, the statistical variation in the number of electrons that are produced by a photon of any given energy. There's noise associated with that as well. Now, next I'll talk about photon counting. This is what's allowing us to achieve the sensitivity that we need on our signal measurements. And this is uniquely enabled by the EMCCD over standard CCD devices. essentially what we're doing is we're taking advantage of that multiplication process to boost our electrons coming into that multiplication register above the read noise. And this is illustrated in the figure on the left. You can see in green, this is the output distribution for actual events that were generated in our imaging section. In this blue curve, this is the read noise. So we can see by setting a threshold, we can exclude a large portion of the read noise and be counting most of the real events. Now, something to consider is that there is some overlap. And so what we have to do is we have to account for that undercounting in our signal processing. Simultaneously, we also need to consider coincidence losses. So in photon counting, each time we see an event above this threshold, so maybe here, or here, or here, we count that as one electron, because that's what we expect to be input into our output register. But if there are two electrons, we're not going to discern that from a one electron event, so we get an undercount. So how we deal with this is that we limit the signal level to less than 0.2 photons per pixel per readout. And so this makes it that the chance of a coincidence loss happening are very low. Now we can see here descriptions of the different signal noise ratios that we can achieve for the different readout methods that we can employ. So we have at the bottom our standard readout, and we can see our major noise sources reflected here. Shot noise, dark current, CIC, so this isn't significant for standard readout. And then finally, our read noise. And this is something that gets applied for every single pixel that we read out. It will typically be the dominant noise source unless we have a whole lot of signal. Now, for our application, we don't have the opportunity to build up all that signal. So something we can consider is analog mode. And what this does is allows us to simply apply that gain and mitigate the impact of the read noise. And so when we have a large mean gain, that divides out the read noise, and this value becomes very small. However, because of the statistical variation in the multiplication process, that does introduce something called the excess noise factor, where because we are boosting these electrons, but we're not quite sure what they get boosted to, we have to account for that statistical variation. And this is equivalent to essentially cutting the quantum efficiency of the detector in half. So that's not too great for our purposes. So we can go a step further, and we can apply photon counting mode. In this mode, we're using thresholding to completely get rid of the read noise, so we don't see it here. Instead, what we have is this additional term where we have the detection probability. And this is what captures things like coincidence losses and thresholding errors and allows us to compensate for that. Now, this table on the right, this is capturing a sample analysis of our instrument where we can see 4 different stars that we considered as a target, just how much we're able to improve the SNR we can achieve. So compare for this first star, Alpha Canis Majoris, we can get 250 signal noise ratio with photon counting versus about 7 for standard readout. So this is very useful for our instrument design. Now, one thing to consider when applying EMCCDs in a space environment is that the high energy particles that are present do present something of a challenge. Now, on the right here, you can see this is dark frame data. So no light was being put on the detector when these images were taken, but we still see all of these events popping up on the screen. And those are actually muon strikes on the detector, and they're depositing large amounts of energy, creating many electron hole pairs in the detector that we actually see saturate and then bloom all the way down the column that we're reading. So this was data taken on the ground. You can imagine it will only be so much worse once we get up in space. And so this is just one impact. The other impact we have to consider is that these high energy particles aren't just depositing the many electron pairs that we have to read out, they can also just fundamentally damage the detector. So this can result in degradation in CTE, increase the dark current level, increase the CIC rate, and also create trap sites. And these trap sites can go in and trap charge as you're reading it out, and then just release it sometime later. And so now you have charge being injected into random places in your readout where normally it shouldn't be. So these are the important considerations for EMCCDs. Now we've kind of gone over what an EMCCD is and how it works. I'll be talking about the model that we developed in order to try and simulate EMCCD operations. So this is a model that we implemented in MATLAB, and as it stands, it's able to simulate all the different processes that we discussed, things like charge generation, charge collection, charge transfer, charge measurement, as well as those noise processes. And it's able to do this at the pixel level. So we can look at individual pixels and say, let's degrade performance here. Let's increase the dark current, maybe it's a hot pixel. Let's degrade CTE, maybe it's damaged by high energy particle strike. And we can look at the effect that has on the operation. Now, in creating this model, the approach we took was to make it physics informed, which is to say it is realistically simulating all these effects. But we're not going in and saying, here's a voltage that we are applying to this pin. Now let's calculate how the electron is accelerated, and let's calculate, does impact ionization occur? Rather, we rely on statistical models to describe this and put it in terms that we can actually measure in the lab. So the diagram on the right is a good representation of how this model works. So we have an individual pixel object that we bring together into a larger detector object that coordinates these pixels into imaging section arrays and serial readout arrays. And so from here, we're able to do, again, these different processes, charge generation, collection, transfer, and measurement, until we are able to back out our final image readout, and then we can be free to do whatever we want with it, whatever image processing we want to perform, save it, do what we want. We also have a third object, the controller, which is responsible for coordinating the actions of the detector. We'll get into the functionality of what this controller object does in a second. Now, as we move forward, you're going to see a lot of text on some of these slides, but don't worry, I'll try and keep it to the most important stuff. So the pixel object, as I said, this is the lowest representation that is available in our model. And this allows us to specify the individual pixel properties, things like the IQE and the quantum full well capacity, which sets how large our charge cloud can be, CTE, dark current, all that sort of stuff. And what this buys for us is the ability to, again, get that level of fidelity to look at individual pixels. Next, we have the detector object, and this is what's coordinating the charge transfer process between these pixels. So clocking out the pixels in both the parallel section and the serial section, and then performing the charge measurement. So we can actually clock these pixels any way we want. We can do it forward, backwards, between the parallel and serial section. We can use the thumb train. This allows us the fidelity to be able to program in any readout sequence that we want to simulate different readout sequences. So if we say we want to integrate for 1,000 seconds to do a readout, we can do that. Or if we want to simulate different characterization methods. So things like actually measuring the detector bias, the dark current, CIC, we're able to do that. And we'll see what that looks like a little bit later in the presentation. Next object we have is a controller object, and this is what's coordinating how the detector is doing those different readout moves. This object is also responsible for applying things like the camera gain constant, which takes our charge cloud and the number of electrons and translates that into a digital number. It is also what's responsible for actually coordinating how the detector is read out and storing that information for when we want to use it. So here at the controller level, we can set various things like the ADC resolution, ADC offset if we want it, as well diagram on the left here, this gives a quick example of how the code actually flows. So when we start the program, what we see is we can configure the detector pixel properties, and then optionally, we can further modify those properties. So we can randomly degrade pixels in the array, do whatever we want with them to get what we want. And then we can start looking at actually operating the model. So we can load our input photon rate maps, which describes how the photons are actually arriving at the detector. And then we can be performing our readout sequences. So doing integration steps, we're simply collecting light charge on the detector, doing transfers, doing measurements, all of that stuff that's necessary to simulate EMCCD. And then we can look at simulation outputs. And this is really that image processing step, and it could be whatever the user wants. So on the right, we have a table that quickly just summarizes how we are simulating these different processes, but I will discuss that sort of as we go. So I'll be sort of stepping through step by step how these different things are simulated. We're going to start with charge generation. So we have incoming photons in the detector. These are specified by a map on the imaging section for each pixel of the mean photon incidence rate. So we use this along with the Poisson distribution to simulate the shot noise. Now, something that we also take into effect is the interacting quantum efficiency. And for that, we just use a binomial distribution to determine for however many incident photons we have, how many of them are successful for the specified interacting quantum efficiency. Now, the next thing that we simulate in charge generation is the phantom noise. So this is related to the quantum yield. I won't go into all the details here, but essentially how we treat the quantum yield depends on the wavelength region that we're working with. For longer wavelengths with lower energy, the quantum yield is essentially always 1. So that's what we set it to in our model. For photons that are less than 350 nanometers in wavelength, but less than 10 electron volts of energy, what we do is we use values for the quantum yield that were measured in the literature, along with the model that we see here for the quantum yield, where we have quantum yield being equal to 1 plus a probability of generating an additional electron volt pair, plus the probability of it generating an electron volt pair squared. And this allows the model to generate up to 2 additional electron volt pairs for the interacting photon, and capture, again, some variability in how the quantum yield is being applied, which gives us our phantom noise. Now we can actually adopt something a little bit simpler for photons with greater than 10 electron volt energies by just using an expression to calculate what the quantum yield should be. So that's eta I here in this equation, along with the full width half maximum that we would expect for the distribution in the number of electron volts being generated. We can use that just to inform our model, get the correct statistical spreads on the electron volt pairs being generated. Last but not least, in charge generation, we also have the dark current. And this just takes some mean dark current rate that was specified for the pixel, and for however time step that we're considering, uses the Poisson distribution to generate those electrons at the charge cloud. So the charge transfer process, that's being coordinated by our detector class. And here we're using the charge transfer efficiency that we're specifying for each pixel to again inform a binomial distribution on what is the success rate of the transfer process. Now I'll also talk about charge multiplication here. So we're using a model that was described in a paper by Basden in 2003. And so what this does is for each electron multiplication pixel, that has a certain probability of multiplying the electron. So again, what we're doing is we're going to be applying a binomial distribution and use that probability of multiplication as our probability of success to get back out the expected electron gain behavior. And we can see a comparison in this chart that we saw earlier, where the histogram data that you see sort of faded in the background, that is being compared to the solid lines that you see here that match up with that nominal theoretical output PDF that we saw earlier. And we can see they agree quite well. So in these simulations on this order of less than 1% agreement. And so we can see that the process that we implement here agrees well with how it should work. And that allows us to capture things, again, the gain being applied, but also that excess noise factor that we want to capture. In the charge measurement process, this is, again, just something that occurs at the end of either of those output registers. Our model can work with either the EM register or the standard register. So if you want to model EMCCD or standard CCD, just depends on which function you're calling. But as a part of the charge measurement process, what we do is we go ahead and add in the ring noise. This is something we model with a normal distribution. So some variance is specified for the detector. And then we can also apply a bias level. As part of this process, also, we have the application camera gain constant and the digitization by the controller object. Now, there are some assumptions and limitations that have gone into this model. So the first is that the CCD response is linear across pixel charge levels. Now, this works well for where CCDs are typically operated at. The response is usually linear. But as we continue to fill up that potential well and reach our full well capacity, we can see some of these properties change in a nonlinear manner, but that part isn't reflected in this model right now. Another thing that we have assumed is that charge collection is perfect. So any charge that is being generated in that pixel is going to be collected by that pixel, rather than, say, diffusing over to a different pixel. This has some effects that we'll look at for characterizing our model. So the last thing that I'll mention is that pixel size is also not represented here. So it's not explicitly tied to how much dark current is being generated. Charge diffusion light gathering area that in reality is dependent on pixel size. But here we're not modeling explicitly. So now we can see some results of actually modeling, of running the model itself. So here we just have a little demonstration where we have inputs for different photon wavelengths. 1 nanometer, 10 nanometer, 215 nanometer, 300, 600, and 1000. And we're reading that out of our model using this made up example interacting Coulomb efficiency curve here. And we can see the results popping out on the right. So we can see that for the inputs that we've specified, we have gotten back out our PT NSI logo, which is exactly what we expect to see. Now, we can also see here a hit from the 1 nanometer input map. So this is a little reflection of how the model works. Now, take a little bit more of a detailed look. We can see this GIF running here. So this is just working with a input photon map spelling out the BT logo. But we can see that we have degraded certain pixels. So on this top left chart, we have degraded the dark current performance of certain pixels, greatly enhancing how much dark current they're generating. In the bottom left chart, we can see that we've degraded the charge transfer efficiency of certain pixels, going from 6 nines for the yellow all the way down to 0.9 for the blue. And we can see in the output image how that has smeared our VT in the horizontal direction as a result of mainly these 3 pixels in the serial readout register. We can see how the readout process is working by this animated GIF. So every single transfer is being modeled in this simulation. And that allows us to achieve this sort of fidelity where we can be tracking how the charge is actually moving through the model during the readout process. something I will note is that for this demonstration, we're using a very small CCD, 12 by 12, rather than the full 1000 by 1000 or even 4K by 4K CCDs that you see, because that would be an absolutely massive GIF file to save. And it'd probably be running for a couple hours before you saw one readout. But, so we saw in the last two slides, our EMCCD model looks like it's working correctly, but we need to make sure that just because it looks right, is it actually right? And so what we're going to do is we're going to look at first some camera characterization that we did with an actual camera in the lab. So we can see here's what a real EMCCD does. And then we're going to try and simulate that same camera characterization in our model and see if our simulated EMCCD behaves like the real one. So what we did was we have a new EM-N2 camera with a Teledyne E2B CCD 201-20 that we were characterizing in the lab. And we used liquid nitrogen to cool it all the way down to -85 degrees C so that we could get something representative of the dark current that we expect to see in the application. So what we did was we collected data for the camera bias. We took photon transfer curve data. We took data to help us characterize the induced charge. And we also took data to help us characterize the dark current. We're going to look at each of those over the next couple of slides. The first is the bias data, and this is data that we collect just by setting an integration time of 0. So we're just immediately reading out that data. And now the dominant process that we expect to see is read noise. And that's largely what we get. We can see in this bias data, in this bias histogram here. However, something that we'll note is that we actually do, in these raw bias frames, see some additional structure going on than what we'd expect from just pure read noise. So we can see a somewhat dark band here on the left with a little bit of a brighter band right next to it. And so this is something that is actually occurring in our detector that's present in our bias frames. Now, next thing we can look at is the photon transfer curve. So a photon transfer curve is generated by exposing our detector to increasing light levels and integration times. And what this does is it builds up the signal over the pixels and allows us to compare how the noise is growing versus the signal. Now, when we have low signal levels, what we see is that the dominant noise process is again read noise. And so we can actually pull out from these low signal values what that read point for is. However, as we build up more and more signal on our detector, we actually see it enter into a new noise regime, where it is instead shot noise that dominates. Now, using this equation from a book called Scientific Charge Coupled Devices by James, we're actually able to relate how our signal level is changing and how our noise levels are changing in order to pull out that camera gain constant that we discussed. Now, as our signal increases further, what we are eventually going to see, what we sort of see going on at the end of this chart here, is that our pixels are actually starting to saturate. And so this behavior becomes slightly nonlinear. If we were to take this even further to higher signal levels, what you would see is the noise level actually begins to drop as pixels become saturated. And so we were able to actually pull out the read noise and the camera gain constant for the camera that we were characterizing. So we have a camera gain constant about 17.8 electrons per digital number, and RMS read noise of about 5.22 digital numbers, or about 93 electrons. Now we can use that data, and we're going to use it to help us find our CIC information. So in this camera characterization method, what we do is we collect 1,000 frames with an integration time of 0 and a gain of 1,000. And what this does is by setting an integration time of 0, we are mitigating the dark current on top of mitigation that we've already achieved by cooling it all the way down to -85. Because essentially, dark current doesn't have any time to generate. And also because we're using a gain of 1000, we're able to mitigate the frequencies. And this leaves CIC as a dominant noise process. And so we're able to actually calculate what the CIC is for the detector. And so probably the most complex slide, but don't worry, most of it is just defining symbols. So what we can do is collect our CIC data into an output histogram. So comparing the digital number outputs to how often they occur. And we can actually use our probability distribution function that characterizes our multiplication process, fit that to our CIC histogram data, and pull out how many CIC electrons we are measuring, as well as the mean gain. And so one thing we can look at here, this is again just that output probability distribution function. When we consider that n, the input to the gain register, is 1, this simplifies down to the exponential distribution function. So we're able to use that and fit it to the data. Now, because of the CIC rate is low enough where coincidence losses are negligible, so we're able to be confident in setting n equals 1 without too many problems. So applying this, we're able to pull out a CIC rate of about 0.003 electrons per pixel per frame. And this compares well to the nominal 0.002 that we could expect from data sheet for the same propagation we are running at. And we can also see that our gain estimate from this fitting process well approximates the nominal 1000 gain we applied with a measured gain of 995. Now we can actually use the same process for the dark current data that we collect. However, what we are now doing is collecting data over a longer integration time. So here 100 seconds, and again applying that gain of 1000. So with a integration time of 100 seconds, that gives the dark current plenty of time to generate within the detector. And so dark current becomes the dominant noise process over read noise and shot noise that aren't present in this data. So what we can actually take a look at here before moving on is if we look at the histogram for our dark data, we see our large peak here. That's the read noise and most of our dark current. But then we also see a second peak. This is where the gluon strikes are saturating those pixels. You can see that effect in the histogram. Now, because of the process that we are using, where we are fitting to portions of the histogram, specifically between 6 times the variance of the read noise and 20 times the variance of the read noise, we actually exclude this contribution from the muons in calculating our dark current. However, if we look at this GIF that's playing here in the top right, we can see that these muons are actually leaving trails on the detector. So we can expect some small contribution from picking up those smears from that charge. However, it shouldn't be too much. And the number that we come back with should be representative primarily of the dark current. So we can see the dark current estimate that we're coming up with is about 7 times 10 to the negative 4 electrons per pixel per second. And again, that compares somewhat favorably to what was given in the data sheet, as well as what was measured for other EMCCDs of the same type. Now, something to note is that when we're looking only at the dark bias data, we can actually identify where some hot pixels are occurring. And these are pixels with enhanced dark current generation. So there's a couple that we see. So 2 occurring here in the middle, but then also quite a number of very high pixels with very high dark current. And again, we can see our gain estimate compares favorably to our nominal value of 1,000. So we've collected some of that primary data for the new view camera. Now what we can do is we can use that data and use it as input to our EMCCD model, and then simulate all those different camera characterization methods and see, do we get back out similar numbers? If we do, that means our model is behaving like it should. If we don't, that means something's not working. So a quick note here, just giving the different model parameters that we're looking at. Now for our model, we are running with a reduced parallel section size. Here, only using a 50 by 50 pixel region compared to the 1000 by 1000 that we're working with the detector. We've also made a approximation number of multiplication elements. Now, a number of multiplication elements, as we saw in the equation for output probability distribution function, does have an impact on what that function looks like. However, what we'll see is that it's actually small enough where we can get away with modeling 50 pixels and still have our EMCCD behave like it should. So first we can look at the bias data, and here we get back pretty much what we would expect just from our description of the model so far, which is a well-formed Gaussian with a bias level of 5. And that's what we see. Now, something to note is that we don't see that same structure that we saw in the real bias data, where we had that odd behavior to the left of our detector. So that's just something to note. For our photon transfer curve simulation, we can see that we are getting out a well-formed read-noise regime, as well as a well-formed linear region. Now, one thing to note is that unlike our real EMCCD, because we have not simulated those non-linear effects, we don't see a very realistic performance when we get up to saturation levels. Instead of having those detector parameters change as we reach saturation, what we instead see is an immediate collapse down to the read noise level as we reach the top of that full bell capacity. However, for the characterization that we're hoping to do, we're actually able to get out fairly accurate numbers. So we specified 5.22 digital numbers for our read noise and a camera gain constant of about 17.7, and we get out those numbers pretty closely. Now, something that we're actually able to do with the same photon transfer curve process is quantum yield measurements. And so when we consider different light levels, different wavelengths of light, we get back out a different. Now, we didn't have the hardware in the lab to do this. However, we can still demonstrate it with our model. And we can see, we can actually calculate the quantum yield from the camera gain constant that we determined in the last slide, as well as this constant J. And this is the camera gain constant that's multiplied by the quantum yield. So we can use that same photon transfer curve process to determine what J should be, and then calculate quantum yield. And so we can look at that for two different wavelengths, 175 nanometers, 0.21 nanometers. And we can see we get out about the correct number for both of those. Now, something to note is that for 0.21 nanometer light, in reality, we don't expect to get out the nominal quantum field value. And that is because in a real detector, not all of the charge as generated by that photon will be collected by that pixel. And so we would actually expect something closer to 1420 electrons versus the nominal 1620 that we calculate from our literature values. So we can see in our simulation, we essentially retrieve that nominal value. However, again, because we're not simulating charge diffusion, in reality, we would expect a lower measurement. So moving on to CIC, we're going to simulate this because we are taking 1000 frames. We're just going to use a 25 by 25 pixel region. These results we see here, we again apply the same processing technique that we use to determine the CIC for the real camera. And we see that we back out, again, a relatively close value. So measured CIC, 0.0031, simulated CIC, 0.0027. And we see that our retrieved gain is again about correct at 1073 versus 1000 that was specified. And we can repeat this process for the dark curve and see that we're able to again pull out similar values. 7.06 times 10 to the negative fourth was measured, and we retrieved from our simulation about 7.8 times 10 to the negative. And again, a retrieved gain of about 1080 versus our specified 1000. So overall, our simulated EMCCD does indeed behave like a real EMCCD. So that gives confidence in the work that we've done so far. It allows us to focus on making further improvements to the model to expand on some of those elements that I mentioned, where we had made assumptions or recognized limitations. So what we would like to do in the future is focus on including models for pixel blooming and charge diffusion, extending models to actually represent traps that might form under individual pixels, allow us to model at a higher fidelity what radiation damage might look like, as well as looking at including things like a cosmic ray simulator that we can include sort of what we saw in the measured data, where we had those very bright impacts and trails being formed. And we're also going to try and extend our ability to model time dynamic conditions. So photon input rates that vary with time, mean incident photon maps that might be changing to say a point of light moving on the detector. These are all things that we would like to try and include in our model as we continue development. I did want to say a quick acknowledgement to Dr. Vijay, who helped us by reviewing and providing feedback as we were developing the model. And then we also have this code available from GitHub. And so the link is included here. We also have this QR code if anyone is interested. Here are some references. Okay, so that's it from me today. If anyone has any questions, I'd be happy to answer.
I did see Dr. Harding joined us there just a few minutes after we got started. So yeah, Leon, Dr. Harding, I don't know if you have anything in particular you wanted to add or ask or that kind of thing as well.
Hey guys, great job as always, Nicholas, and yeah, I really enjoyed joining here. It's been a lot of work on Nicholas's part here, so looking forward to reading his thesis this weekend actually. So good job, guys.
Thank you. Yeah, any questions, anybody? I'm trying to put you on the spot because
I don't know how much I understood, but I wanted to ask why what about the saturation? You planned on doing the saturation, defining saturation, or
so including some of those linear effects is also on the docket to be included. It's really a challenge just looking through and figuring out, how best to represent these. And of course, there are additional things that we want to consider, which is how can we make our model generic? So there are many different EMCCDs that are available. We want to make sure that our model is able to represent, as generic a one as possible to make it as useful as possible. So part of the challenge is also just going through and seeing what is a result of device-specific work, what is a general pattern, and how can we represent that general pattern in a way that can be tested in the lab and then specified in our model.
using for cameras.
Yeah, getting more hardware is always more fun. I was going to maybe ask a quick follow-up. What have you seen, or what do you expect? How like the nonlinear effects, or maybe you presented. I think you talked some of that about like nonlinear. Maybe again, like a summary on that, like what do you expect will be kind of impacted by?
So essentially what you start to see, I think actually a great way to visualize it by looking at these muon strikes. So at the heart of these is these bright white central regions. This is where saturation is occurring. And so part of the nonlinear effects is that as that potential well fills up, you actually start to get charge spilling out into the other pixels that are in the same column in the imaging section. So one thing is to figure out how do we best represent how that spilling process occurs. So just deciding we have an electron being generated. Is it going right? Is it going left?
Yeah,
Our left, right. The one on the left has saturated. So we have two saturated pixels next to each other. Now where are they going? Just figuring out how that works and getting it represented in the model. And of course, one of the challenges is also making sure when we're developing this that we can get it to run in a reasonable amount of time. That's another challenge with development, trying to make sure that we are simulating every single transfer, and as you increase the detector size, that results in potentially thousands of transfers being modeled. So the individual calculations have to be fast. And so whatever features we want to include, we also need to think about how efficiently we can include them.
Yeah, otherwise I don't think I had any other questions. Any other questions? We'll conclude it there for now. Thanks so much for Leon for joining. For the people, we'll have our last seminar for the series or for the semester in 2 weeks, and I believe Jenny Smith, a PhD candidate, will be joining us to talk about balloon path prediction. So, otherwise, everybody in 2 weeks.